11 years ago, there's something quite interesting because 11 years ago, we, the College of Science, decided to create this lecture series because there was a court case in Pennsylvania in which they were trying to add intelligent design to the curriculum of the schools in Pennsylvania. And it went up to the courts. The courts decided that intelligent design was not science. But we here decided at that point, even before that court did what they had to do, we decided that it was really important that people, that the public, that all of us should really understand the facts that then we're asked to give opinions about. Reminds me of the very famous saying of Patrick Moynihan. It says we're all entitled to our facts, we're all entitled to our opinions, but we're not entitled to our facts. So 11 years ago, we started in the Center for Creative Photography, where there are 250 seats, and clearly there was enormous interest in the topic, and then we just continued. And interestingly enough, 11 years since, we're here debating facts. So I think more important than ever, it is to come for all of us to understand truly what the facts are, make our intelligent opinions on the facts. So more important than ever, lecture series like these are quite topical. So this lecture series is funded by great folks in the community that I think we should all appreciate. Tucson Electric Power, let me just say them all and then we can give an applause to all of them. Ventana Medical Systems, the Arizona Daily Star, Cox Communication, Galileo Circle, and if any of you want a good seat, join the Galileo Circle and also support the community through your efforts. Godot Design, Halua Loa Companies, the Marshall Foundation, Wynn and Tarbit Patent Law, Raytheon, Research Corporation for Science Advancement, and Vantage West Credit Union. How about it we just give them all a big round of applause? So for 10 years, we've been pushing the envelope of describing interesting facts that we now know as scientists, which in fact are central to the debates that we are in the policy and political arena. Last year was about global climate change, for example. We've talked about the genome. All of you have had some skirmish with one or the other, and we can go on and on. Facts are important, and that's what this lecture series is all about. So now we're really getting into, and by the way, the title of Rethinking Reality was before the election, so it has nothing to do with politics. It has to do with physics, but you can make your own opinion about the facts. And today we're going to talk about how physics, since the inception of physics, has been trying to understand the universe that we live in, and how, as we move farther and farther away from what we really observe, what we're evolutionary-wise capable of accepting, coming to the opinion or coming to the conclusion that the universe is incredibly weird. So today, Keith Dienes is going to give us a presentation that will try to set up the lectures for the rest of the time. We're going to have 5 of these lectures about how physics behaves at very high pressures and temperatures, what the quantum world is all about, what the very small world of particle physics is all about. All of that is what I hope we will all learn about today. So Keith received his bachelor's from Princeton, his master's and PhD from Cornell, came here to the U of A after he held a postdoc positions at McGill University in Montreal, at the Institute for Advanced Study in Princeton, and at CERN in Geneva. This is typical of our faculty members here in the College of Science. Most recently, Keith has been engaged in public service, and he's a program director for the Theoretical High Energy Physics and Cosmology at the National Science Foundation in Washington, D.C., where he oversees the funding of fields across the entire U.S. and helps to develop federal science policy in these fields. Keith's primary interests are in theoretical high-energy physics, He focuses on new ideas for physics beyond the so-called standard model of particle physics. These ideas include supersymmetry, grand unification, large extra dimensions, and ultimately string theory. Most recently, he has been developing a new approach to the dark matter problem. You'll hear throughout this lecture series that astronomers and astrophysicists have decided that most of the universe is made out of dark matter and dark energy, so there's no poetry in it, but that's what they know, and he's working on that. His results have been featured in Scientific American, The New Scientist, Science Magazine, and Physics Today, and he's a fellow of the American Physical Society. Please help me welcome Keith Dienes. They're all yours.
Well, it's a pleasure to be here. I'm really happy to see a large audience. I won't say it's the largest ever existed, maybe, but it certainly is gratifying to see so many people interested in science, and that's what's great, I think. So this year, the University of Arizona College of Science lecture series will be focusing on some extraordinarily big questions. And you see them here. What are the fundamental building blocks of the physical world? What are the different kinds of glue that hold these building blocks together? What happens at the extremes of matter and energy, space and time? What are the laws that govern the behavior of all things, large and small, seen and unseen? Where do these laws come from, and what do they tell us about the birth and death of the universe and everything in between? So, through the upcoming weeks, 4 physicists will be here, in addition to me, to tell you about their cutting-edge research that pushes the frontiers in attempting to understand and answer these questions. But we had organizational meetings to plan this lecture series, and as we were talking, we felt that something was lacking. Most people, we thought, really have a general idea of what chemistry is or what biology is, but what exactly is physics? How is physics different from the other sciences? What are the big ideas in physics? Is there a corresponding big picture that physicists carry around in their heads when they think about the natural world? So that's really going to be the goal of this kickoff lecture. Rather than tell you about my own research, which I will not do, I'll instead aim to provide a leisurely tour through some of the most cutting-edge concepts in modern physics. And taken together, all these ideas are shaping the big picture that physicists have ultimately formed about the universe and the laws that govern it. And this is ultimately part of how physicists are currently rethinking the rules of reality. So this won't be Physics 101, the ideas won't be elementary, rather this will be Physics 500, really the cutting edge concepts, but all explained hopefully at a very non-technical level. So that's the goal. Now, the title of my slide is Rethinking the Rules of Reality. And this is, if you think about it, a rather strange title. It has 3 components: rules, rethinking, and reality. And in this lecture, what I'd like to do is discuss each of these in turn. But first, we should start with what physics is. What is physics? If you go into the street and ask a random person walking around to name the most intelligent person who ever lived, you might get, and people do this, often on late-night talk shows, you might get a lot of responses, Shakespeare or Bach or Mozart or Beethoven or maybe Charles Darwin. But far and away, the number one answer is a physicist. And you all know who he is. So if you start to narrow the question down and say, well, amongst living people, who is it? The number one answer, again, is another physicist. This is Stephen Hawking, a British cosmologist. If Hollywood wants to portray smart people, what do? Again, they make them into physicists. Plus an engineer without a PhD, but he's allowed to hang around also. If you ask people, what are the most famous equations in all of science? Well, they also are equations that come from physics. E equals mc squared and F equals ma. What is the reason for this fascination with physics? Ultimately, I think it's because physics is different. Physicists tend to view the world in strange, abstract ways. And I want to give you some examples of what I mean by this. If you study how the gravitational attraction of the sun causes the planets to move in stable elliptical orbits around it, you're likely to be an astronomer. And astronomers have done this for many, many years. If you study how the massive forces involved in tectonic shift cause mountains to rise and the earthquakes to occur, you're likely to be a geologist. If you study how an organism swims through a fluid using its flagella, or how a hummingbird beats its wings so as to remain stationary above a flower, you're likely to be a biologist. If you study how the electric fields involved in forming chemical bonds prevent the individual atoms in a molecule from moving around freely, thereby forming a stable crystal, you're likely to be a chemist or a materials scientist. But a physicist? Well, a physicist looks at all of those situations and says, well, in each case, there's a force being applied to an object. And that force results in a certain change in the motion of that object, either creating motion or maintaining equilibrium. Let's just study the notion of force as an abstract entity, and let's also just study motion and equilibrium as abstract entities. We don't need to specify whether we're talking about planets, or continents, or hummingbirds, or chemical bonds. And now we can ask the general questions. How is force related to motion? When do forces produce equilibrium? When don't they? Note that we're seeking universal truths, abstract truths, statements about how the universe operates at all times, in all places, in all circumstances. These are the physical laws that we seek to uncover, the physical laws that underpin all things, and we're seeking to understand their consequences. This is physics. Now, I've said physical laws, but in fact, these physical laws are nothing but the rules that we're talking about, the rules that govern the natural world as we know it. So let me give you an example. You've all heard this equation, F equals ma. It's the discovery of Newton. It's his so-called second law. What it means is that forces acting on objects cause them to accelerate. Now, it turns out that this is true no matter what the object is, no matter what produces the force. Now, this law may seem obvious, but for 2,000 years, humanity was confused about this and actually believed something different. What was believed was that forces were necessary to induce and sustain motion. That's wrong. Instead, we now know, since Newton, that forces are only necessary to change motion, not to cause it or sustain it, but to change it, to produce acceleration. It's the job of physicists to propose such laws and to test them in a variety of circumstances. Ultimately, through repeated experimental confirmation, we come to believe in the validity of a law as a universal truth of nature. I'll give you another Newton-based example. This one is a little more interesting. We just saw the apple fall through from the tree, from the earth to the earth from the top of the tree. It's the usual well-known story that Newton sat under the apple tree and the apple fell and hit him on the head. And he then, according to the story, realized that this is the result of the same force, gravity, that's responsible for the moon orbiting the earth. But you've heard this story, but you may have thought, how can that be? The moon never crashes into the earth like the apple. These appear to be different phenomena. What Newton realized in that moment is that they're not. In each case, gravity does the same thing. It pulls an object directly towards the center of the earth. Now, for the apple, that was the only motion there was, so that's all that occurred, and the apple just fell directly to the earth. For the moon, however, there was another tangential velocity already existing. The moon was already moving parallel to the Earth's surface tangentially toward the horizon. So the combination of falling and that tangential velocity together traced out that curved orbit. But in each case, gravity, the gravity part was universal, and it does only one thing: it pulls toward the center. The commonality and universality of physical law the idea that the same principles might underlie different phenomena is not always obvious, as we see from this example. As in the case of the falling apple versus the stable lunar orbit, the phenomena themselves might look very different, and they might have vastly different implications. Now, if we were content to understand each phenomenon separately on its own terms, which is fine, but we might then miss the deeper common structure. It's the job of the physicist to probe more deeply and uncover and discover the commonalities that underlie the workings of the universe at their deepest and most abstract levels. Now, all good science really starts with observation and then classification based on similarities and differences. However, physicists aim to do something further. To extract underlying principles, the underlying physical laws, the rules that we've been talking about, even if they look different in different contexts, as in the apple case with the moon, and then to use these physical laws in order to predict phenomena which are not yet seen, perhaps with energies or sizes or temperatures which have never been probed before, or in new settings which have never been explored before. Sometimes the laws of physics, as we formulated them, then work well in these new contexts, and we say, great, we believe in it even more. However, sometimes they don't work well in these new contexts, and they then require reformulation into new, more general laws whose scope of validity is even larger than they were before. Thus, laws are not abandoned. We don't just say, oh, we thought it was true, but now it's completely false and we throw it away. Instead, laws are constantly incorporated into bigger, more complete structures, and this is how our field advances. Now, as with any branch of science, input from experiment is critical. Scientific progress, especially in physics, is a dialogue between experiment and theory. Experimentalists communicate directly with nature. They're the ones who actually talk to nature directly because they take direct measurements. Nature talks to them. It's a special role, really, for experimentalists. And they do this by building sophisticated experiments in the cleverest ways in order to extract data. By contrast, theorists then take this data and interpret it in terms of the physical laws and the fundamental principles they've developed. If necessary, they hypothesize extensions of these laws and principles. They then propose new ideas and predictions which experimentalists then proceed to test. Thus, the field really walks on two legs, shifting back and forth between experimentalists and theorists. Now, many fields of study have people who tend to be more involved in a laboratory setting and people who tend to be maybe more running numerical simulations or working on blackboards. But physics tends to be one of the most extreme in having a dichotomy between experimentalists and theorists, to the extent that almost no functioning physicist today does both. And it's a shame. But we need such specialized training that very early on, when you're growing up and you're a would-be physicist, you know in your heart you're either going to be an experimentalist or a theorist. Most of us choose when we're undergrads or maybe graduate students. I was in charge of our graduate program admissions here for a long time at the U of A in the physics department. And one of the first things you look at when you're opening a folder for an applicant is this going to be an experimentalist or is this going to be a theorist? Because this is right away the first most important question that you want to know about the person. It identifies them. Now, I've been talking about understanding the fundamental laws, but that's not all. As you know from, for example, playing chess, you can know the rules that govern how each piece moves, and still you have no idea how to play the game, have no concept of the grand strategies that will result in victory. There's more to actually playing a game than knowing these fundamental rules. And similarly, in parallel with the process of discovering new physical law, physicists also have to do something else. They work hard to use these laws with increasing power and sophistication in order to understand and predict phenomena of ever-increasing complexity across the entire spectrum of science. Everything from material science and chemistry and biology, all the way to astrophysics or nuclear science or quantum science or engineering or complexity theory. In each case, what one finds is that new emergent phenomena can appear that might not have been anticipated based on the fundamental laws alone. Having more elements in your system, having more produces different behavior. More leads to different. Physicists nevertheless study all these behaviors from their uniquely abstract perspective. Thus, I think it's fair to say physics sits at the foundation of most sciences that deal with the natural world. Now, historically, physics has gone through many major upheavals in which a set of laws were recognized not to be complete and were slowly and painstakingly understood to be mere special cases of more general laws. This has caused physicists to continually rethink the very nature of the rules that govern the universe. This is the rethinking part. Now, we don't do this randomly. In general, as we grope to develop new, more sophisticated rules, we're guided by a number of profound concepts that seem to underlie almost everything we know about the natural world. One important guide that physicists use is symmetry. And I'm sure you all have an idea of symmetry. Symmetry is everywhere in the natural world. There are many different kinds of symmetry. Here's a left-right reflection symmetry. The left side and the right side are the same. If you just put this picture in a mirror image, it would look identical. There are other kinds of symmetries, rotational symmetries, threefold symmetries, fourfold, the cloverleaf, fivefold, as in the jellyfish, sixfold, as in the tapestry, ninefold, that is an aerial view of a Baha'i temple in India, tenfold, that is a diamond. There are other kinds of symmetries, for example, lattice symmetries, where again, if you know a fundamental cell, it fills out the whole plane in the same way. There can be cylindrical symmetries where you have a symmetry about rotating around a central vertical axis, as in the tin can or in the vase. Finally, you can even have the spherical symmetry. Here's an example of a sphere. Now you could ask, why are symmetries so important? Why does nature care about symmetries? Well, there's one, I think, very profound reason. Symmetry produces pizza. No. Symmetries are important because I think they allow us to describe a lot of information about an entire object using only a little bit of information. For example, if an object has a left-right symmetry, then if I tell you everything you need to know about the left side, you already know the right side. It's very efficient. If an object has a rotational symmetry like the pizza, then if I tell you what's happening in one slice, or one wedge, you already know what the whole thing is like. In case of a lattice, you know the entire picture just by describing one central cell. So nature, I think, loves symmetries because of the efficiencies they encapsulate. However, as we'll see, physicists also love symmetries because they simplify the situation and they enable us to solve problems that might be too complex to solve in other ways. Now, there's another idea that guides physicists when we're looking to understand how to rethink things, and that has to do with conservation laws. And the basic idea is that in certain situations, a physical quantity, some number, some quantity that we use to describe the system, is conserved. And what that means is that even though the system may evolve and its characteristics may change as a function of time, certain quantities that describe the system are nevertheless the same or fixed at all moments in time. And perhaps the easiest example, the one you're most familiar with, is conservation of energy. If, for example, consider a pendulum. What's happening is that the height that exists at the edges is, by the time you come to the middle, traded. You lose height, and instead you gain speed. So height is traded for speed and back and forth. Something is conserved, because we don't have height when we have speed. It's traded back and forth. What's conserved is the total energy of the system. The ideas of symmetries and conservation laws are very old ones in physics. They go back to Newton. But remarkably, it wasn't until the early 20th century that a connection was actually found between symmetries and conservation laws. In my opinion, this connection represents possibly the most profound discovery in all of theoretical or mathematical physics. And it states nothing more than if a physical system exhibits a continuous symmetry, then a corresponding quantity must always be conserved. In other words, for each symmetry, there's a corresponding conserved quantity, and vice versa, a corresponding conservation law. So two of the deepest concepts in theoretical physics, symmetries and conservation laws, are actually fused into one. I'll give you an example of this. Here we have an experiment that we are preparing to do maybe at 8:20 in the morning. Most scientists are not in the office at 8:20 in the morning. Let's make this PM. And they do the experiment. And they drop the thing in, and it turns yellow, and they say, aha. Okay. Now, they may repeat the experiment later at 10:10, and again, drop it in. They should get the same results because the laws of physics should not care whether the experiment was done at 8 o'clock or 10 o'clock. In other words, if the laws have this property that it doesn't matter when you do the experiment, then this connection I was telling you about says that there's a conserved quantity, and the conserved quantity is energy. And this system must conserve energy. So somehow time is connecting to energy. Completely mysterious, but this is what this theorem tells us. Now, this connection between symmetries and conserved quantities really does represent a fundamental observation and theorem. It's actually a theorem proven mathematically about how nature works at the deepest, most abstract level. And as you might imagine, the ramifications of a theorem like this reach to any physical system that can be imagined, determining what processes may occur and which ones not. The ones that conserve the conserved quantity would, and the ones that don't conserve the conserved quantity cannot occur because they would be violating the conservation law. Although this theorem was originally formulated in classical Newtonian mechanics, it extends readily to relativistic situations and even quantum mechanics. Its implications extend across all of physics, from subatomic physics to entire galaxies and everything in between. In fact, I'm not the only one who thinks this is an amazing result in theoretical physics. Two physicists who recently wrote this book have said, this is certainly one of the most important mathematical theorems ever proved in guiding the development of modern physics, possibly on a par with the Pythagorean theorem, which is about the sides of triangles, proved by the ancient Greeks. We're saying for 2,000 years, this might be the most important result. So you might wonder, who is the physicist who actually discovered this? Why haven't you heard of this person? Well, this is her name. She's Emmy Noether. She was born in Erlangen, Germany in 1882. She studied mathematics, but only by special permission because it wasn't permitted for women in those days in Germany to study a subject such as mathematics. So she had to get special permission, but she did, and got her PhD from the University of Erlangen. They were happy to keep her working in their research facilities, but without pay, of course, for the next 7 years, before she moved to the University of Göttingen, also in Germany, where she spent the next 4 years lecturing under the name of male colleagues. They felt that, well, she couldn't teach a course by herself, so she had to pretend that she's substituting for somebody else. Again, this was the prejudice against female physicists at the time. But she did this, and her fame was readily apparent, and she had loads of students who wanted to follow her around campus, taking whatever courses she was teaching. Her fame grew in both mathematics and physics, ultimately culminating in her plenary lecture to the International Conference of Mathematicians in 1932 in Zurich. This is a big deal. But when the Nazis dismissed Jews from faculty positions in Germany, she had to escape, and so she moved to Bryn Mawr College in the US and died 2 years later in 1935 of complications from surgery for an ovarian cyst. So died in midlife, so wonder what she might have done if she had lived longer. When she died, the New York Times would not publish a eulogy, but Albert Einstein felt compelled to at least write a letter, a tribute, And he wrote that in the judgment of the most competent living mathematicians, Fräulein Noether was the most significant creative mathematical genius thus far produced since the higher education of women began. That's high praise coming from Albert Einstein, no less. So using ideas like these, physics has advanced through many different conceptual revolutions. Each one called for a radical rethinking of the fundamental rules of the game. So what I'd like to do now in the next part of the talk is just take a quick, brief tour through some of these conceptual revolutions in physics. My list is not complete. I'm sure other people would have put different items on the list and taken off from the list. But this gives you a sense of the kind of rethinking that we're constantly having to do as physicists. So of course, our field, like many things, starts with the ancient Greeks. In some sense, they were important because they were the first to ask the same kinds of questions, the fundamental questions, that we ask. But our field really got going with the Newtonian revolution in the late 1600s. This is the modern birth of our field. What it did was it established a clear mathematical set of principia, principles, upon which the entire structure of the universe was supposed to rest. Another big breakthrough, here I'll attribute this to Maxwell. Maxwell was a British mathematician and British physicist in the mid-1800s. He worked on electromagnetic theory and fused electric and magnetic phenomena into a single framework, which we now call electromagnetism. Before him, people believed that electric fields and magnetic fields were distinct, separate things. But what we've learned now is that if an electric field varies in space, it's different in different places in space, or different in time and it fluctuates, then that immediately pops into existence a magnetic field. And likewise, if a magnetic field varies, that pops into existence an electric field. Together, they're unified to produce electromagnetic waves. This was his big discovery. And not only that, the electromagnetic waves move at the speed of light. So somehow now there's a deep connection between electromagnetism and light, which hadn't really been understood before, but now it becomes apparent. Another great development was the atomic principle, the idea that matter is discrete. Before this realization, matter was considered to be a dense, continuous pudding-like substance. No matter how much you zoomed in and looked at little pieces of it and broke them apart and looked at further little pieces of it, it always appeared to be a continuous pudding. This is what people believed would be the case. But we actually know now that matter is ultimately made of discrete atoms, and each atom is mostly empty space. That's kind of strange. Another major development had to do with what I'll call statistical mechanics and thermodynamics. This is also the late 1800s. This is Newtonian physics applied to the realm of the very many particles. And when you have very many particles, they can have a temperature. And what was believed at the time was that, well, people knew about heat, but they didn't know that heat was a form of energy, that it can be traded back and forth for other kinds of energy, like kinetic energy or potential energy. But this was the discovery, that heat is another form of energy. That enabled the development of the laws of thermodynamics and the recognition that systems tend to evolve in the direction of increasing disorder. And I'm sure many of you are familiar with this phenomenon. Your desk never happens to get neater by itself. Things evolve in the direction of increasing disorder. You'll be happy to know this is a law of physics. And you can use that as an excuse anytime somebody says, why are things always getting messier? But it's true. If you see a glass of milk fall off a table, shatter on the floor, and the milk goes flying in all the different directions, and you run the movie backwards, you would find that the milk would collect and the glass would pop up onto the table. You know which way is the correct direction of time for the movie. But the reason is because of these results. This sets a preferred direction for the flow of time. The physicist who really pioneered this was named Boltzmann. And he was very concerned about this. He had developed this result that there was a preferred direction, but in order to develop these results, he used Newtonian equations. Newtonian physics has the property that if you take time to minus time, if you run the movie forward or backward, it doesn't make a difference. If two billiard balls collide that way, that's the same thing as if they collide that way. Newtonian physics doesn't really seem to care. And yet he somehow, when considering lots of particles, found that systems tend to evolve in the direction of increasing disorder. He was giving public lectures on this. This was his major life work, his biggest result in his career. And one day somebody asked him from the back of the audience, but wait a minute, you started with equations that had this property that you could run the movie forward and backward, and now you're claiming there's a result that there's a preferred direction. How can that be? He didn't know the answer. He worried about this for a long time. Eventually, this drove him to suicide, which is not a good example of work-life balance. And also the reason why perhaps I'm glad there won't be a question and answer session after this. Another revolution that happened rather quickly was special relativity. This is Newtonian physics extended to the realm of the very fast. And here what you found were remarkable things. No matter how long or hard you push on an object, you can never make it go faster than the speed of light. That's not expected. People moving with different velocities seem to see the same objects as having different sizes. So if I'm looking at a house and I see it has a certain size, but somebody on a train moving by looking at the same house would say it has a different size than I see. Speed distorts reality, but this is also what special relativity tells us. Another major intellectual rethinking that had to occur has to do with general relativity. This was 1916, this is Einstein as well as the previous one. This is Newtonian physics extended to the realm of the very massive. Gravity, it turns out, is nothing but the bending of space and time. Now, that's weird enough, I'm not even going to try to explain that. Subsequent lectures by Sam Gralla and Ferial Ozel will talk about this. But this is the foundation of all of modern cosmology. The Big Bang, the expanding universe, black holes, event horizons, gravity waves, it all comes from here. The quantum revolution is another one I'm sure you've heard of. This developed slowly over many years, but it finally reached its crescendo in the mid-1920s. This is Newtonian physics extended to the realm of the subatomic. And the basic idea is about matter. Is it a particle or is it a wave? Sometimes it behaves like a particle, sometimes it behaves like a wave when you go to the subatomic world. In particular, one weird thing one finds is that identical experiments will follow the same laws of physics, but need not produce the same outcomes. You can have an experiment here and an experiment there, they're identical. And they follow both the same laws of physics, and yet this one says A at the end and this one says B. In fact, all that can be predicted, it turns out, are the probabilities that you'll get A or get B as the end results. Absolute determinism was lost from physics at this moment. You'll hear more about this quantum weirdness in the lecture by Pierre Maistre at the end of this lecture series, but this is what he'll be talking about. Another major revolution has to do with quantum field theory. This is quantum mechanics joined with special relativity. And what we learned from here, through all these kinds of weird diagrams that you often see people draw, physicists often are playing with diagrams like that, is the discovery of antimatter. For every particle, there's a corresponding antiparticle that it can annihilate with. And in some sense, this is finally the dream of alchemy. This is modern alchemy. One particle can be annihilated, and a completely different particle, a different element, can be created in its place. The vacuum, which is just another word for empty space, can create particle-antiparticle pairs out of nothing. This, again, was a very strange concept. Now, such revolutions have continued even to the present day, causing a continual rethinking of the ultimate nature of reality. I could have continued that story with things that happened in the 70s and 80s and 90s, and I will, but I want to put this in the last part of the talk here, because what we're interested now to understand is then, well, if we're continually rethinking the ultimate nature of reality, where are we now? In particular, what describes the reality of the universe as we understand it today? So now I want to switch gears a little bit and tell you the big picture we think we have today about the nature of the physical world? What are the fundamental things? Well, when I ask a question like what is fundamental, I really am asking for two things. I'm asking for what are the fundamental particles that make up the matter that everything is made of, and what are the fundamental forces that describe the interactions between the different particles of matter. But even the use of the word fundamental is a bit strange and time-dependent. If you think about biology for a minute, you might say, well, the fundamental object in biology is the cell. And for a long time, people thought that. But then we came to understand that maybe the nucleus had a lot of very special role to play. And maybe within the nucleus, we discovered DNA and began to think that maybe that was fundamental. Chemistry, similarly, one might have thought compounds, but then actually molecules and maybe individual atoms and atomic structure. For physics, what is the corresponding analogy? What are the different things that are fundamental to us? Well, it turns out that what's fundamental to a physicist depends on the energy scale with which you probe, with which you look. If you look with more energy, you might see smaller and smaller distances. Why? Because in general, it takes more energy to probe smaller and smaller distances. So if you're looking with more and more energy, you might see different fundamental things. So the energy units we're going to use to tell this story are called EV. And this is just a code. It stands for something called electron volt, but basically all you need to think of is that this is the natural energy scale associated with atoms. Okay. So the fundamental particles at different energy scales, well, at the EV scale, the electron volt scale, the fundamental elements are atoms, in particular nuclei plus electrons that orbit around them. But it turns out, as you know, that there are different types of nuclei that exist. These fill out the different elements, the periodic table. And if you go into any chemistry classroom, or maybe you remember from your own chemistry experience, in your own high school classroom, you saw the periodic table, and it was arranged in certain rows and certain columns because there was certain repeating structures that made sense to arrange it this way. There was a structure to it. That structure suggested that there was, this repeating pattern suggested that there was a deeper structure, and indeed there is one. To probe this, we go to higher energies, mega electron volts. This is a million times stronger. And at this level, we see that a nucleus is actually a collection of protons and neutrons. And so those different arrangements of protons and neutrons with different numbers of protons and numbers of neutrons, that's what makes the different elements and fills out the periodic table. Okay, so at the MEV, the mega electron volt scale, we would say, well, the elementary particles are protons and neutrons, plus those electrons that are orbiting. And you might think that for a while, but it turns out that there are many different types of neutrons and protons. These are collectively called hadrons, and you don't just have proton and neutron, but you also have pion and kaon and rhomezon and omega, lots of Greek names. This was all discovered around the 1940s, 50s, 60s. People were discovering these like mad. Couldn't even keep up with a naming scheme. And people said, well, once again, there seems to be a repeating structure. Maybe there's something deeper. And we looked with higher energy machines, colliders usually, at the giga electron volt scale, GeV, and we found that inside each proton were 2 up quarks and a down quark, and inside each neutron were 2 down quarks and an up quark. And so now at the giga electron volt scale, the fundamental particles appear to be quarks, plus those electrons again. But once again, these powerful colliders found that that wasn't it. There were many different types of quarks, not just up and down, but also, and we had to give more names, so here they come, strange and charm and bottom and top. You could feel the desperation. Likewise, it turns out that those electrons also were just the beginning of a series of particles that were all very light. They're called leptons. Lepto is a Greek prefix. It means light. And so these are light particles. So there was not only the electron, but a slightly heavier one called the muon, and a slightly heavier version of that called the tau, and then 3 different other light particles, which are called neutrinos. And they're listed here as nu sub e, nu sub mu, and nu sub tau. Electron neutrino, muon neutrino, and tau neutrino. They seem to go with the other leptons, the electron, the muon, and the tau. For the remainder of this talk, I just want you to note that there are 3 neutrinos, and they come in different types: electron, muon, and tau neutrinos. So again, you'd suspect there must be a deeper structure. So of course, you're dying to know what it is. And if we had built the superconducting supercollider that you might remember that people used to talk about building in Texas about 20 years ago, if that had been built, I could probably tell you now. But it was canceled, and so we don't know. So this is as far as we've come so far. And we wrap up our knowledge in what we call the Standard Model. And the Standard Model, here it is, very simple. It consists of the particles that we just saw, the quarks, up, down, strange charm, top, bottom, and the leptons, electron and its neutrino, muon and its neutrino, tau and its neutrino. These are grouped in packages of 3 generations. Each row is like a generation, and we say that there are 3 generations of quarks and 3 generations of leptons. That's the particles, and along with this are the forces. And there are many forces. There are 3 fundamental forces, it turns out, 3 primary forces. And they each have different strengths, which are listed there in relative numbers. The strongest one, with a strength as big as 1/8, that's called the strong force. Its job is to prevent the atomic nuclei from exploding due to electrostatic repulsion. Think about this for a minute. You learned in chemistry, when you learned about an atomic nucleus, that it's made of protons and neutrons. Well, here's a question you could have asked your teacher, and probably your teacher wouldn't have known the answer. But here's the question. If the neutrons are electrically neutral and the protons are all positively charged, then really you're shoving all these positively charged objects together, but we know that like charges repel. So this thing would want to go flying apart. What then keeps an atomic nucleus together? The answer is that you're right, the electromagnetism wants to make the nucleus fly apart, but there's another force which is even stronger. It's this strong force which is attractive and holds it together. Then there are 2 other forces, the weak force and the hypercharged force, and as you see from the relative strengths there, they're much weaker. These 2 forces work always together. They're very coupled in a certain mathematical way. And the best way to describe what they do is, the best way you know that they're there, especially in Arizona here, they make the sun shine. So we in Arizona owe our uniqueness to these forces. Now you might say, but what about electromagnetism? None of those forces that I listed are in electromagnetism. Well, it turns out that the weak force and the hypercharged force are like blue paint and yellow paint. But if you mix them together, you get green paint. Electromagnetism is like that green paint. It's not a primary color, it's not a primary force. The primary forces are weak and hypercharged, but they can be mixed together, and that's what electromagnetism is. It's just a mixture of these 2 more primary forces. And the thing that does the mixing is that magic Higgs particle that you've heard about. So, if you want, there's a certain grammar to the Standard Model. The particles are the nouns, the things that get acted on. The forces are the verbs, the things that do the acting. And the Higgs modifies those verbs and how they behave. It's an adverb. And if you want, you could imagine the Standard Model as having those 3 forces, and you can imagine listing them on an axis according to their strengths. We'll list the strongest ones at the bottom and the weakest ones at the top. So there's the strong at the bottom, and then the other 2 further up. Now, you might ask, is that all there is? But there's lots of reasons to believe in something deeper. The Standard Model has many parameters you have to put in. You have to say, what is the mass of every one of those quarks and every one of those leptons? You just have to measure the number from data and put it into your theory. We would have liked to predict something like that, not just measure it from data. So that's a bit mysterious. There are also conceptual questions in this standard model. Why do the particles come in 3 generations like that? Why are there 3 kinds of forces? Why do these forces have those different strengths? Again, you would have hoped a fundamental theory would explain that, but we don't have that in explanation. We just measured it, and those numbers are what they are. And that's not really very pretty from a physics point of view, where you want to understand fundamental reasons for things. And then finally, there is another force you know about, gravity, which we haven't even mentioned here. How do you incorporate the gravitational force? How do you quantize gravity and put it into this framework? So once again, we think there should be, we suspect that there is a deeper structure. So to go beyond the standard model, we have to build big accelerators. And fortunately, after 20 years of planning and building, the next generation of accelerators and colliders and detectors are yielding data now. And what I'm showing here is an overview of the Geneva countryside. This is just outside Geneva, Switzerland. In fact, right here behind me, this white stretch here is the runway of the Geneva airport. So you get a scale here. These are many different towns. I used to work, before I came to the U of A, I worked at this European Laboratory for Particle Physics, which is just outside Geneva, Switzerland. And you would know every day as you drove in and out, inside the ring and outside the ring. Of course, the ring here is all underground. And we underground accelerate particles and make collisions and then look at the debris and try to figure out what the next level of nature might be. I mentioned that when we do these collisions, we have to have detectors to see the spray of particles that come out and measure them. And one of the big detectors is called the Atlas detector. I mention it because our research group here at the U of A was very instrumental in building that Atlas detector and affecting its overall design. So, you'll hear more about this in the subsequent lecture from Elliot Chu. But what kinds of physics do we expect to find at these colliders? Well, this is now speculation, but this is what most people believe. So this is part of our big picture. One idea is something called supersymmetry, often called SUSY. And this is a new kind of symmetry in physics, and basically what it says is that for every one of the standard particles that you saw before on the left, the ones that make up the standard model, there's a corresponding supersymmetric partner. And that's a lot of new particles. But the reason we imagine this is because it would help to solve a lot of puzzles. It would help to explain the relative strengths of the forces, why the strong force is so much stronger than the weak force and so forth like that. It would help to explain why the Higgs particle, it turns out to be much lighter than we expected. And it could even possibly explain dark matter. So supersymmetry is one theory we really believe that we will find, and we actually believe that we'll find it at an energy scale just slightly higher than the standard model, just a little bit higher up. So this horizontal axis that I'm building is going towards increasing energy, and we believe that supersymmetry will come right beyond there, just beyond or at the reach of current accelerators. Searching for supersymmetry was actually one of the primary reasons the Large Hadron Collider, this big circular ring in Geneva, was built. The next idea beyond supersymmetry is what we call grand unified theories, where the forces would, at very high energies, unify into one. And at first glance, it might seem that such a unification of forces couldn't possibly happen because the 3 fundamental forces had different strengths. But it turns out that for various reasons, as you go upwards in energy, the strong forces become weaker, the weak forces become stronger, and they actually do unify. It's rather remarkable. So this number, 10 to the 16 of those GeVs, giga-electron volts, this would be the natural energy scale for grand unification. Finally, at the very highest energy scales, physicists think the world is governed by string theory. Now, what's string theory? This is a complicated subject. I can barely tell you, but let me give you a cartoon which I think captures the essence. The basic idea is that if you looked at an elementary particle like an electron under some really powerful microscope, you would find that what it really consists of is a vibrating loop of energy, not a point particle, but a loop. It would have structure. And all particles and forces in nature would then be unified because they would be different excitations of that fundamental loop. And higher vibrational modes would correspond to the quarks or the leptons or the forces that we know, or even gravity. So therefore, everything would be unified as different excitations of one fundamental entity, which is the string. So string theory sits at the highest possible energy scale you can consider. And it's the hope that string theory would then provide theoretical guidance concerning the many possible extensions to the Standard Model that would fill this desert as we move upwards in energy scale from what's down there on the left, where current accelerators can reach, and what's up here on the right, which are the fundamental scales of physics. This desert is mysterious to us, and maybe string theory could give us some information about that. So this was the picture that we carried in our heads, certainly until the 1990s. When I went to grad school, this is where I would have ended a talk. But in the last 20 years, again, we've had to do some rethinking. So let me conclude this talk by telling you the 4 things that have changed this picture and what we now think the new picture is. So the first big result in the late 90s were those neutrinos. It turned out, when I went to grad school, we were told the neutrinos were massless. No more. We now know they have very tiny masses. Thus, it turns out neutrinos can do something no other particle can do. They can change their identities as they fly through space without interacting with any other particle. And remember I told you there were 3 kinds of neutrinos? An electron neutrino can be flying along and it says, hey, I'd like to be a muon neutrino now. Oh, I want to change to tau. Oh, I want to be an electron neutrino again. And they can oscillate like this through space. That's weird. No other particle can do that. Another big discovery, of course, was the discovery of the Higgs boson. For the first time, this allows us to study important phase transitions in the Standard Model, like water melting into ice. There are other kinds of phase transitions in the Standard Model, and this enables us to probe, for the first time, the underlying ground state. Now, those are 2 things that were about the Standard Model. But it turns out, even more mysteriously, that over the past 2 decades, we've learned that the Standard Model itself does not describe the entire reality of the universe. Even more exists out there. In particular, there's been a dawning realization. It was not a sharp discovery, but a dawning realization with more and more evidence accumulating that there is something called dark matter. Now, first of all, I want to emphasize right away, dark matter is a bad name. Because it's not really dark like a black hole sucking in all light, but rather transparent, in the sense that everything we know moves through it invisibly. We know it's there because we can feel it gravitationally through its gravitational effects on other objects in the universe, but we have no idea what it's made of. We don't even know if it interacts with itself or whether it goes through itself transparently. We don't even know that. It's a complete mystery. Yet, it turns out that this, dark matter, whatever it is almost 26% of the entire energy of the universe. Here I've shown what's called the bullet cluster. The red regions are regions that are high in ordinary matter, very dense in ordinary matter. The blue regions, and we've just colored them blue because dark matter is transparent, but by gravitational sensing, we know that this is where we believe the dark matter is, and you see it sits there right alongside but separated from ordinary matter. It's a real object. Okay. The other most incredible discovery, this happened in 1998, and this was a complete surprise, is that unlike dark matter, there's something called dark energy. Unlike dark matter, this permeates all of space and acts like an anti-gravity in the sense that it causes space itself to expand more and more rapidly. Because of the dark energy, it's now believed that the universe will expand forever with an ever-increasing speed, faster and faster, rather than approach a stable final size or shrink back down into a final crunch. We didn't know what the universe might do eventually, but now because of this dark energy, we think we know. But what physics makes up this dark energy? We have no idea whatsoever. Your guess is as good as mine. Even worse, the dark energy comprises A little bit? No. 70% of the total energy of the universe. So the final big picture I want to leave you with is this pie chart. We call this the cosmic pie. This is the total energy distribution of the universe. That yellow slice is normal matter. That's the standard model I told you about. That's everything we know. Planets, stars, the entire visible universe, you, me, Tucson. We all reside in that little slice. The dark matter is that purple, 26%. It's not in the standard model. It's currently a complete mystery. And then dark energy, we have no idea at all. And that's 69%. Boy, this is a rethinking, if ever there was one, when we thought that 5% was everything. So I hate to do this to you, but what that means is that this talk ends only with mysteries. And that's the nature of science. Answering one set of questions only poses more. But these are really exciting times to be a physicist, as you'll see from the subsequent lectures, because we're all constantly rethinking the rules of reality and probing the most fundamental questions about the composition of the universe and the laws that it obeys. So I urge you to stay tuned to scientific developments as they occur, and most importantly, I'd like to see you at next week's lecture when my colleague Feryal Ozel will take you to the extreme limits of our physical universe. So thank you very much.